Hey there, viewers! Welcome back to Dr. Carminati's YouTube channel, where we unravel the mysteries of cutting-edge science and technology to empower you with knowledge that sparks curiosity and innovation. If you're new here, I'm so thrilled to have you join us. Today, we are diving deep into the quantum world to explore quantum coherence and decoherence, their impact on cybersecurity, and the solutions that could safeguard our digital future. I'd love to hear your thoughts. Drop your ideas for future videos in the comments. Share your reactions, hit that like button, and subscribe with the bell icon to stay in the loop. Let's build a community of explorers and thinkers together. Ready to quantum leap into this topic? Let's get started. Introduction to quantum coherence and decoherence. Quantum mechanics governs the strange and fascinating behavior of particles at the tiniest scales, and two key concepts, quantum coherence and decoherence, lie at the heart of this realm. These phenomena not only shape the future of quantum computing, but also pose significant challenges for cybersecurity in the near future. Understanding them opens the door to a new era of technology and security threats we must address. In this video, I'll break down what quantum coherence and decoherence are, explain how they create problems for cybersecurity, and highlight solutions that researchers propose to tackle these issues. Whether you're new to quantum mechanics or a tech enthusiast, this journey will equip you with a clear understanding of these concepts and their real-world implications. Let's dive into the quantum deep end and explore what makes this topic so critical. What is quantum coherence? Quantum coherence describes a state where a quantum system, like a qubit, the building block of quantum computers, maintains a perfect balance of multiple states at once. Imagine a spinning coin that's neither heads nor tails but both simultaneously. This is called superposition. Coherence allows qubits to exist in this superposition, enabling them to perform many calculations at once, a feature that gives quantum computers immense power. For example, a qubit can represent both 0 and 1 at the same time. When multiple qubits entangle, a phenomenon where their states link together, they create a vast computational space that classical computers can't match. This coherence relies on maintaining precise phase relationships between these states, meaning the system stays undisturbed and isolated. The beauty of quantum coherence lies in its ability to enable quantum interference, where different quantum states combine to amplify or cancel each other, much like waves in a pond. This property enables quantum algorithms to solve problems, such as factoring large numbers or simulating molecules, exponentially faster than classical systems. However, coherence is incredibly fragile. Any interaction with the environment, even a stray photon or a slight temperature change, disrupts this delicate balance. That's where decoherence enters the picture, threatening not just quantum computing, but also the security systems we rely on. What is quantum decoherence? Quantum decoherence occurs when a quantum system loses its coherence due to interactions with its environment, causing it to behave more like a classical system. Picture that spinning coin again. Now imagine air molecules bumping into it, forcing it to land on heads or tails. That's decoherence at work. In technical terms, the environment is entangled with the quantum system, causing the superposition to break down. The qubit's wave function, which describes its quantum state, loses its phase relationships, and the system transitions into a statistical mixture of classical states, like 0 or 1, but not both. This process happens because no system achieves perfect isolation. Environmental factors like electromagnetic fields, thermal vibrations, or even cosmic radiation interact with qubits, causing them to lose their quantum properties. For instance, a qubit in a quantum computer might decohere in microseconds if exposed to a fluctuating magnetic field. The time a qubit maintains coherence, known as its coherence time, determines how long it can perform useful computations. Researchers note that decoherence stems from various mechanisms, including photon emission, phonon scattering, and spin relaxation, all of which degrade quantum states over time. This fragility poses a significant challenge for quantum technologies, particularly in the realm of cybersecurity, where quantum systems promise both breakthroughs and vulnerabilities. How does this pose a problem for cybersecurity? Quantum coherence and decoherence will create significant cybersecurity challenges, particularly as quantum computing advances. Let's break this down into two key areas: the threat to encryption and the vulnerabilities in quantum communication systems. First, quantum coherence enables quantum computers to threaten classical encryption systems. Many cybersecurity protocols, such as RSA and elliptic curve cryptography, ECC, rely on the computational difficulty of problems like factoring large numbers or solving discrete logarithms. A coherent quantum computer, using algorithms like Shor's, solves these problems exponentially faster than classical computers. For example, a quantum computer with enough coherent qubits could break RSA encryption by factoring a 2048-bit key in hours, a task that would take classical computers billions of years. This capability, as discussed in the Medium article Quantum Tunneling and its potential in cyber attacks by Rocket Me Up Cybersecurity, could enable attackers to decrypt sensitive data, such as bank transactions, government secrets, or personal communications, posing a significant risk to the global cybersecurity infrastructure. However, decoherence complicates this threat. Quantum computers require sustained coherence to execute these algorithms, but decoherence disrupts their qubits, introducing errors that render computations unreliable. While this might seem like a natural defense, it's only temporary. As quantum hardware improves, coherence times will extend, making these attacks more feasible. The article also highlights a related concept: quantum tunneling, where particles bypass cryptographic barriers probabilistically, could amplify this threat. Attackers might leverage tunneling to accelerate decryption, exploiting coherence to breach encrypted channels before decoherence sets in. This dual nature, where coherence enables attacks and decoherence hinders them, creates a race between quantum advancements and cybersecurity defenses. Second, decoherence directly threatens quantum communication systems, which rely on coherence to ensure security. Quantum key distribution, QKD, utilizes quantum principles such as entanglement to generate unbreakable encryption keys. If two parties share entangled qubits, any eavesdropping attempt disrupts the entanglement, alerting the users. However, decoherence in quantum networks undermines this security. The Medium article notes that attackers could exploit decoherence by injecting noise into quantum channels through tunneling, causing qubits to lose coherence and disrupting secure communication. For instance, an attacker might crowd a quantum channel with noise particles, triggering decoherence that corrupts the transmitted qubits, effectively launching a denial-of-service attack on a quantum network. Additionally, decoherence enables more sophisticated attacks, such as entanglement hijacking. Attackers could manipulate the coherence between entangled qubit pairs, intercepting or altering data in a quantum man-in-the-middle attack. This vulnerability, combined with decoherence's role in degrading quantum states, makes quantum communication systems a prime target. As quantum networks grow, managing decoherence becomes critical to maintaining their security, especially since even small environmental interactions, such as temperature fluctuations or electromagnetic noise, can cause significant disruptions. What solutions are suggested? Researchers and cybersecurity experts propose several solutions to address the challenges posed by quantum coherence and decoherence. Let's explore these strategies, which aim to protect both classical and quantum systems in this evolving landscape. To counter the threat to classical encryption, experts advocate transitioning to post-quantum cryptography, PQC. PQC includes algorithms resistant to quantum attacks, such as lattice-based cryptography, which relies on the complexity of high-dimensional lattice problems. The Medium article emphasizes that lattice-based systems offer resilience against quantum tunneling and other quantum attacks, making them a promising defense. The National Institute of Standards and Technology, NIST, leads efforts to standardize post-quantum cryptography, PQC, algorithms, ensuring they can secure data even as quantum computers scale up. Organizations must adopt these algorithms now, as the transition requires updating software, hardware, and protocols, a process that could take years. For quantum computers themselves, mitigating decoherence is key to both their functionality and their potential threat to cybersecurity. Quantum error correction codes, QECC, help maintain coherence by encoding a logical qubit across multiple physical qubits, allowing systems to detect and correct errors caused by decoherence. Surface codes, Shor codes, and topological codes, as mentioned in Breaking Down Quantum Decoherence Challenges and Solutions from Quantum Zeitgeist, provide robust frameworks for this. These codes tolerate errors without compromising information integrity, extending coherence times to enable longer computations. For instance, topological codes encode information in a two-dimensional lattice, making them inherently fault-tolerant against environmental noise. Beyond error correction, Researchers employ environmental isolation techniques to reduce decoherence. Quantum computers often operate at cryogenic temperatures, near absolute zero, to minimize thermal vibrations, as seen in D-Wave's quantum annealers, which use liquid helium refrigeration to maintain stability, according to Decoherence, Quantum Computers' Greatest Obstacle by Matt Swain. Electromagnetic shielding also blocks stray fields that disrupt qubits. Photonic systems, like those developed by Quandela, offer another advantage, as photons interact weakly with their environment, providing naturally longer coherence times, as noted in Quantum Decoherence, Quantum Computing Explained by Quandela. Dynamical decoupling techniques further suppress decoherence by applying rapid pulses to qubits, counteracting environmental interactions. Quantum Zeitgeist highlights that these methods create a noise-free band around the system's characteristic frequency, preserving coherence. Additionally, coherent feedback protocols, as explored in noise suppression via coherent quantum feedback from Science Direct, regulate qubit dynamics without measurement, driving noise-affected states back to their desired trajectories. These strategies collectively aim to extend coherence times, ensuring quantum systems remain reliable for computation and communication. For quantum communication, solutions focus on preserving entanglement over long distances. Single-photon quantum frequency conversion to the 1550 neon telecom C-band, as discussed in From Quantum Communication Fundamentals to Decoherence Mitigation Strategies from Science Direct, minimizes transmission losses in optical fibers, reducing decoherence in quantum networks. Entanglement distillation also helps by maintaining entanglement despite environmental noise, ensuring QKD systems remain secure. These methods strengthen quantum communication channels against decoherence-induced attacks, safeguarding sensitive data transfers. Quantum coherence and decoherence are more than scientific curiosities. They're shaping the future of cybersecurity. The race to harness coherence for quantum computing while mitigating the disruptions of decoherence will define how we protect our digital world. Dig deeper by exploring NIST's post-quantum cryptography standards or researching companies like Quandela that leverage photonic systems. Think about how these concepts could impact your own data security. Could quantum-resistant algorithms protect your online transactions? The quantum era is here, and understanding these phenomena empowers you to navigate its challenges and opportunities. Stay curious, ask questions, and let's keep exploring this quantum frontier together. What a thrilling dive into quantum coherence, decoherence, and their cybersecurity implications. We've unpacked their definitions, explored their challenges, and highlighted cutting-edge solutions. Now, I want to hear from you. Drop your thoughts, questions, or video ideas in the comments. How do you think quantum tech will shape cybersecurity? If this video sparked your interest, give it a thumbs up, subscribe, and hit the bell for more fascinating content. Let's keep this conversation going and inspire each other to innovate. Until next time, keep exploring, and I'll see you in the comments.